So, hi and welcome to your introduction to HDL. This topic discusses week 3 to 4 gate level modeling. Okay, so so here a circuit is specified by its logic gates and their interconnections. Okay, so it provides a textual description of a schematic diagram. And Verilog recognizes 12 basic gates as predefined primitives. Okay, so we have 4 primitive gates of 3 state type. And of course, we have 8 other, okay, which are AND, NAND, OR, NOR, XOR, XNOR, NOT, and BUF. Okay, so when the gates are simulated, the systems assign us 4 valued logic sets to each gate. So we have 0, 1, unknown, or either X, and high impedance, or Z. Okay, so when a primitive gate is incorporated into a module, we say it is instantiated in the module. So in general, component instantiations are statements that reference lower level components in the design. So essentially, creating unique copies or instances of those components in the higher level module. Okay, so thus, a module that uses a gate in its description is said to instantiate the gate. So modeling with a vector data, multiple bits with widths. Okay, a vector is specified within a square brackets and 2 numbers separated with a colon. Example, this one. Output, okay, bracket 0, colon 3, D, semicolon. Okay, this declares an output vector D with 4 bits, okay, from 0 through 3. For output, okay, again, wire per wire, okay, bracket 7, colon 0, then sum, semicolon, this declares a wire vector sum with 8 bits numbered 7 through 0. Okay, so the number listed is the most significant bit of the vector. Okay, 2 or more modules can be combined to build a hierarchical description of a design. Okay, so there are 2 basic types of design methodologies. Okay, we have top-down. Okay, in top-down design, the top-level block is defined and then sub-blocks necessary to build the top-level blocks are defined, are identified. Then we have the bottom-up. So here, the building blocks are first identified and then combined to build the top-level block. So in the top-down design, a 4-bit binary adder is defined as the top-level block with 4 full adder blocks. So then we describe 2 half adders that are required to create the full adder. In bottom-up design, the half adder is defined, then the full adder is constructed, and the 4-bit adder is built from the full adders. Okay, so we have a bottom-up hierarchical description of a 4-bit adder is described in Verilog as we have a half adder, okay, defined by instantiating primitive gates. Okay, we have different gates combined to create a half adder, and then define the full adder by, of course, combining the 2 half adders. Of course, finally, the third module describes 4-bit adder by instantiating 4 full adder. So note, in Verilog, one module definition cannot be placed within another module description. So let's proceed with our example. So here we have our example. We have 2 input AND gate. Okay, so you will notice we have A and B and our output. But in our example, we'll be using A1 and A2 as your input, and this is your output. So if you still remember your truth table, okay, example, if your A is 0 and your B is 0, of course, your output should be 0. If your A is 0 and your B is 1, your output should be 0. If your A is 1 and your B or A2 is 0, your output would be 0. And if your A1 and B or A2 is equals to 1, your output is 1. Okay, so we'll start with the coding. Okay, so if you have your Notepad++, first you have to type module. Okay, that will be the start. Okay, and then name your module. Let's since we are testing AND gate, so let's try test. Okay, one. Or let's try test underscore AND. Okay, and then okay, your input A1, A2, and your output B. So that will be our input, and output, since we have two inputs and one output. And of course, type input A1 and A2. Then your output, okay, is equals to B. Then of course, you have to end your code with end module. Okay, then let's try to save this one. File, save as. Okay, if you still remember, you installed your application in C. Yeah, if you can see, C, I, Verilog, and then bin. Of course, you have to install your application also here. Okay, so let's try to save it as test underscore and, because we are testing AND gate. Okay, up. Make sure to include .v. Okay, is this clear? Test underscore and .v for Verilog. Then save. You will notice now, okay, these are all blue codes. Can you follow? Again, module. Okay, this is the start. This is the end module. Then this is just the name of our module. So I named it test underscore and for AND gate. Then we declare our input and output. We have A1 and A2 as input and B as output. So we also declare here. Input is A1 and A2 and our output is B. Okay, so now we're done saving this. We'll now create our test bench. Test bench, okay, we use test bench, of course, to test if our AND gate is working properly. Okay, so file, again, new. Now we'll start with our test bench. Okay, so again, we'll start with module. Okay, and then let's name this as test underscore, okay, AND gate underscore TV, okay, for test bench. Okay, so this is the stimulus program for testing the AND gate. Okay, you can save it again already. Save as, okay, test, okay, underscore and .v, but make sure to and underscore TV. Okay, so we have now our test bench. Okay, so let's start. So next thing we need to do is, of course, we have to declare the input. We will be using reg A1, A2 for your input, and of course, we'll be using wire, okay, for our output. Okay, then we'll use initial. Okay, so initial, okay, so only once we are assigning the values initially through the whole routine. So that's the function of initial, and of course, begin. Okay, so all the blocks of code should always start with keyword begin, of course, and should end with end. Okay, so inside here, we will write some statements. Okay, so example, the A1 and A2 here is just the two inputs for the AND gates, and they are giving different possible combination for the inputs A1 and A2. So why? Okay, to check the functionality of the AND gate, whether it is giving the proper output or not. So our basis will be the truth table. Okay, so since begin, let's try to give a value for example A1. Okay, initial value for A1 is 0. Then initial value for A2 is also 0. Okay, so we have 0, 0. Okay, so then after that, okay, after 3 nanoseconds or 3 time, okay, I want the output I want to change A1, the value of A1 to 1. Okay, and then after 1 nanosecond or 1 time, okay, I want to change the value of A1 to 0. So here, our value here is A1 is 0, A2 is 0. Here, A1 is 1, A2 is 0 because we did not change A2. Here, we change the A1 again. So the value now is A1 is 0, A2 is 0. Okay, clear? Next, after 2 time, okay, after 2 time, I want to change the value of A2 is equals to 1. Okay, and then after 3 time, I'll change again the value of, let's say, 4. I'll change the value of A1 again to 1. So again, here, our A1 is equals to 0, A2 is equals to 1. Now we change the A1, so value here is A1 is equals to 1, A2 is equals to 1. Okay, and then 3, I'll change value of A2 is equals to 0. And then after 1 again, our value is now A2. Here, we're just declaring the values. Okay, it's up to you what values you want to use, but just use 0 and 1. Okay. After that, just type end. Okay, so we're done with uh, the statements. Okay, so now we'll use the formula. Okay, we have here the and. Okay, we already have the existing code inside the Verilog, which is and. Okay, then I'll declare the name as G1 for this end, and then output is B. Okay, A1 and A2 are the inputs. Okay, so and here is the keyword signifying an AND gate. Okay, again, G1 is the name assigned to the specific instantiation. Okay, and of course, A1, A2 out inputs, B are the output. Okay, then we'll be using initial again. Okay, and then we'll use the monitor. Okay, so initial monitor, okay, is used. Okay, this is a system task. Or always keep the track of the values inside this one. Okay, so it will keep tracks. Okay, the value inside. Example, we'll be using so just remember whenever changes happen in A1, A2, okay, will be displayed on the screen. So let's use time. Okay, so and then A1 is equals to percent %B. Okay, and then A2 is equals to percent %B also, and then B is equals to percent %B. Okay, and then we have A1, A2, and B. Okay. Yeah. Okay, now what is the use of time? Okay, so time, it will just display the simulation time or timing on the screen. Okay, if you still remember this one, diba? We created time here. Okay, so let's check later. Okay, and then we'll type again initial, and then we'll use 100. Okay, it means that after 100, okay, well, let's add first the finish. Okay, and then end module. So this means that after 100 nanoseconds or 100 times, okay, it will end. Okay. Okay. So now let's try to run. So again, initial monitor just to monitor the changes in A1, A2, and AB. Okay. So all the values here will be posted here. Okay. So every changes, okay, it will display the value. So to try, again, you still remember your CMD. Okay, just go to CD dot dot, then CD dot dot again. to go to your C prompt. And then now access your Verilog. You can also check if you have your iVerilog here. Okay, now access the iVerilog using cd iVerilog, then access also the bin, cd bin. So now we can test. Okay. So to debug or to compile, okay, what we need to do is type iVerilog -o, okay, and then name your file. Example, I'll name this as and, okay, and then call your this one, the test underscore and dot v. So type test underscore and dot v, and also your test bench. So test, okay, test underscore and underscore tb dot v, and then enter. Okay, so we have error, missing closing quote. Wait, here. Okay, you see, you can also check the error. Then save again. Then run again. Now syntax error. So what's our error? Let's check here. Okay, this one. It should be number sign, not dollar. Okay, save again. Okay, so we ran it successfully now. If you will not encounter any error here, like this one, okay, so it means that you successfully compile. Now to run, just type VVP and use your, this one, the one that you use as the name. So and then run. So what did you notice? We have now our truth table. So this, you still remember this one, di ba? Wait. Can you see both the CMD and the notepad class? Okay. So here we our initial state is 0. So 0 here. And our value is A1 is equals to 0, A2 is equals to 0. That's correct. Okay, A1 is equals to 0, A2 is equals to 0. So based on the truth table, it should be 0. Now, you notice the 3. After the 3 time or 3 nanosecond, our A1 now is 1, which is correct. A1 is 1. And your A2 is equals to 0 pa rin. Okay, so we have A2. And our value now is our B or output is equals to 0. Next, after we add another 1 nanosecond. So 3 plus 1 is equals to 4. That's why it's 4. And then our A1 now we change to 0. So this is A1 is 0. And A2 is still 0. Okay, and then our output is 0. Now, we have 4, and then we add 2. That's why this is 6. Okay, so our A1 now is 0. Okay, so this one is still A1, so nothing's changed on the 2 nanosecond. But our A2 now is 1. Okay, so A1 is 0, A2 is 1, output is still 0. Now, we have 6, then we add 4. So that will be 10 now. Okay, here we change the A1. So A1 is 1. So A1 is 1, correct? And still, the A2 is equals to 1. So A2 is equals to 1. So your output should be 1, correct? If A1 is 1 and A2 is 1, your output should be 1. Okay, and then here, so we have 13 because we have 10 already here, plus another 3 nanosecond or 3 time. And we changed our A2 to 0. So our A1 is equals to 1. Okay, here our A1 is equals to 1. Our A2 is equals to 0. So our output now is 0. Then after another add tayo ng 1 nanosecond, So we have 14 here. Then no change in A1, so still 1. A1 is equals to 1, and we change the A2 to 1. So our A2 now is equals to 1. Of course, our output should be 1. So is this correct or not? And did you notice this one? Finish code at 100 because we initiate, okay? We declared after 100 nanosecond, okay, we will end the program.